And so next, I don't need to introduce David again, but David's going to come back and talk about an issue that's very passionate to me, and that is how we scale all of this stuff up to matter. Thanks, David.
Thanks, everybody. So before I forget, we have a brochure, like all good programs. They're out there on the desk. Please take some so I don't have to take them home with me. Most important. So, under the program over the last 12 months, we've been undertaking a bunch of kind of engineering and scaling assessments across a number of the interventions. I'm just going to talk about one of them today, just to use it as a case example. I'm going to talk about aquaculture as a delivery mechanism. It's a potential delivery mechanism for a number of the things that Lena just went through. And so we wanted to explore some thinking around, well, just what would be involved if we really did want to ramp that up. And look at that, it worked. In this talk, I'm just assuming that magically the broodstock exists. We've found them, we've identified them, we've created them, however. And I'm looking at a process from hatchery to grow out to transport to field placement to deliver reproductive adults. And we set ourselves a goal, a design target of to deliver 35 million corals per year, year in, year out, at an equivalent age of 1 year. So they had to survive, so I needed 35 million at the end of 1 year. That wasn't to say we were deploying at 12 months of age. We could deploy earlier than that, but then you needed to factor in post-deployment mortality across 20 species, generally fast-growing species. And you go, that's a ridiculous number, David. And, well, perhaps it is. But under some of the modelling, we've been looking at scenarios of between 10 and 100 million corals into the system just to understand what that will do, and Ken might talk about that a bit later. And we pulled together a team from some, Woolley Parsons is a multinational engineering company, ourselves, and in fact Secor, to determine what I would refer to as the mass production commodity rate for fast-growing corals based on existing technology and credible, how can I put it, improvements in what we can do now. Things that we have some idea about how we might do, we just haven't done it yet. But not needing magic. I didn't need, Harry Potter wand to make this work. And this was about seeing how we could make this work. We talk about all the challenges and issues and whatever else, but I wanted to identify what would we actually need to be able to do to ramp up to that sort of scale. So what did we do? Well, we did the classic kind of engineering approach, employed a bunch of engineers, and they went out and did drawings of facilities to work out how much land you'd have to buy and what the roof area would be. Designs internally to understand workflows and where you would need automation in this, at various scales, down to some of the automation processes. We then went out and looked at a whole bunch of different delivery options. From the truly enormous, so the ship on the left is a pretty typical pipe laying vessel, where you need a vessel out in the ocean that's got a big accommodation block and a work platform. I talked a bit earlier, one of the challenges we have in the GBR context is the remote location of a lot of these reefs. You can't run a shore-based operation. You cannot go backwards and forwards each day. You need to be out on the reef working, and if that's the case and you've got a big team, you have to accommodate them through a whole range of size vessels. Then we did a bunch of automation studies about how could we use automation to do this. And you take all of that and you do a value engineering approach. And I'm condensing, 6 months of work by quite a few people. And you can use some operations research type methods to start understanding relationships around the cost of infrastructure. You can start playing with mortality inside that process. Inside an aquaculture process, you have a bunch of points where you have mortality and you have reducing numbers. You start with millions and you end up with thousands sort of things. And so you can start playing, where do I accept mortality, or where do I put more effort in? And more effort costs money. It needs more roof space, or I have to have older corals or something like that. We looked at transport, we looked at shipping and deployment options, and we looked at a mixture of sexual and asexual methods to see theoretically how we might deliver out through that process. One of the keys to getting this to work was to be able to deploy in as much of the year as possible. To get that number out the door, I should have done a bit of maths at the start. Obviously 36 million is 100,000 a day. You're not going to be deploying every day. Certain seasons you can't, weather conditions you can't, tides you can't. So you end up doing some maths and you needed to deploy somewhere between 10 and 30 a second in the deployable window. And so you do a bunch of logistics studies. And where do we land? I just want to quickly go through a concept design, then talk about some of the observations that we made along the way. We had a facility, of course, and in fact we split it into 3 sites. We needed to ship the coral in as low a density area as possible, so we came up with the concept of growing corals on these high density boards, and I'll come back to that. If we were going to put it on something, we ran a few different scenarios and we dry shipped that. We needed 2 boats. In fact, we needed 3 sets of what I'm about to show you, so we had 6 of these vessels. 1 on site, 1 running back to pick up new people and new product and bring it out, and 1 on site that served as accommodation. We then put a bunch of off-the-shelf automation on that vessel, so the automation exists. And then we had a flotilla of deployment boats, 7 per pair. So overall we had 6 of the bigger ones and a whole bunch of the smaller ones, running in operation simply to get enough capacity to deploy at the rate that was required. And we've then used this to make a few observations, and we'll use this to think about variance on this and understand stuff going forward. But I did want to go through a couple of key observations. So what did we learn? This thing netted out at about $3 to $4 per coral at 1 year of age, factoring in that we weren't deploying 36 million, we were deploying more under the model that we looked at. And this is a number that takes into account buying the block of land, building the facilities, owning the boats. For some weird reason, they put an interpretive centre in there. The whole cost of capital, running it, insurance, the lot. So this is a standalone commercial facility, plus or minus 50% numbers, and like most contractors, it's probably closer to the plus 50% number at 1 year of age. Just to kind of understand, based on these assumptions, where might you land? Still think it's too expensive, so we'll go back to the drawing board. Nevertheless, we now have a model that we can test assumptions under. We can go, ooh, what if I could do this bit better? What happens if I could improve survival rates here? What if I could, what if I could, what if I could? That's the power of this. Second key learning was that post-deployment survival and growth rates are key. At the highest level, that's self-evident. If you put 1,000 corals out and only 10% survive, then your cost is 10 times more than if they all survive per coral. But it's a bit more subtle than that, and I'll go through it. And thirdly, that's got to standardise modular systems, and automation creates some pretty significant benefits. Some of you will see I've talked about this a bit before. This is a diagram, and on one axis is cost per adult survivor from high to low. So I'm just going, okay, I put however many out, but if a bunch of them die, then this is the cost that I need to amortise across the living corals. And time in production across the bottom line. And if I was to look at a kind of a fairly traditional growing a coral with divers and things like this, where you're tending it for a long period of time, we tend to try and do those until we kind of know that it's going to survive. So we keep them in the production line for a long period of time, and they come out at a particular cost. You know, if you could automate that process, you drive your costs down. The reality is, to get further cost reductions per unit, you simply need to reduce the time in production. We kind of all know that. You know, you buy a Rolls-Royce car, it sits in the factory for 7 months, it costs a lot of money. A Toyota Corolla, 7 hours, costs a lot less. But you run into your type 3 survival curve. Again, talking to a bunch of biologists, you guys get this sort of stuff. And so you end up with this kind of cost barrier that's driven by survival rates and a kind of a minimum theoretical point. And until you break out of that curve, you're kind of stuck. You end up jammed in this spot where, in fact, that's about as good as you can get. And you know, there's a few strategies. The one that we employed in the designs that we were looking at was trying to reduce early life, post-mortality, post-deployment mortality, get your words together, David, if you're deploying younger corals. And so can we do better than nature? Can we deploy corals out at a, sort of 30 days or 60 days of age and still have them growing at a similar sort of survival rate to older corals? And of course, the application of automation. And you kind of get the obvious outcome. You get a drop with the automation, your mortality line, and you get a much lower theoretical number. And in part, that's what we were exploring with this design case, was how sensitive was it to it. And of course, this particular graph is very sensitive to your species of coral, to the location, to the particular circumstance. Nevertheless, it's a bit of a framework to assess what might be possible and start guiding where you put your development efforts to make this occur. Second quick observation was around modular systems and automation. One of the things we quite quickly worked out was that shipping volumes, in this case, became quite material. If we were having corals in a big tank of water and I've got to ship them out to the reef, the volumes are actually quite substantive. If I've got those sitting in an aquaculture facility and I've got a very spread out, one coral here, one here sort of thing, again, big roof line costs money. Space costs money. And so we came up with a thought piece around, could we settle corals onto something that looked like a chocolate block, so we call them choco boards, reinvented. And then when in our aquaculture facility, can we stack those at high density so that we settle onto those and we have a very small footprint? Clearly you can't keep them there for too long because they'll start overgrowing that space. And then can we ship those at high density? So you can stack them at high density, use off the shelf, those are just stock aquaculture, live aquaculture trade deployment tanks. Can I stack those in there to run them out onto the reef? And then I get there, what do I then do with them? And so this is an example of a kind of a variation on the Seacor stars, where we looked at options. Okay, now I can take my board, split it up into its individual little choco bits, and then attach them to a device. We want to do that manually, so we looked at how we might automate that. But you don't have to have that design. You could modularize this type of setup to bigger or smaller things, depending on the benthos that you're trying to place these into. Different size, different shapes, different methods are going to come into play. What about attaching them to something that looked like a Mars spider? Again, the same aquaculture process, the same product that you're sending out. It's a modular design, build it so that it can clip on. We've even gone as far as looking at what happens if I just want to do it with a diver or an automation. This is a bit complicated, but this is a design where you take 3 of those, you attach them to a little screw device, you have a canister, it's a pneumatic drilling arrangement, put it on the reef, drill it in, move to the next spot. If I had an instant glue, it would be a lot simpler. Nevertheless, if you can modularize these things, these sort of options become much easier to do because we're not all then building bespoke bits of kit. You can get into bulk manufacture, so a bit of audience participation. This is one of the Seacor devices. It's about the same size as the device that's on the page there. Show of hands for all those that think that this device, if I got it manufactured, would cost more than $10. More than $1. More than 10 cents. So it's made from unglazed ceramic. It's got 7 components. It's about this size. More than 10 cents. Well, you're all wrong. So less than 10 cents for the whole kit if you do it at bulk. So there's just huge economies to be made if you can standardize and get into some bulk purchasing. But you can also start doing some other things. You can start fiddling with your materials. You no longer then need the same material for your recruitment surface versus things that you're putting it onto it. And you can start playing with algae prevention or anti-predation macro features or microstructures. You can look at high recruitment materials. You could look at embedding slow release compounds. How do you get that improved survival when you're deploying at an early life cycle? Bunch of the reasons are just straight bad luck. I got eaten by something that happened to swim past. Well, you can probably prevent some of those things. We don't want to prevent some of the mortality that's fitness related, but can you prevent some of those other things? And you start being able to play with this sort of stuff. Would I do this at the scale that we're talking about with ceramics? Ideally not, no. The carbon debt's too high. Really want to start looking at natural products. But again, this sort of thinking means that if we can kind of standardize a bit more and modularize, then as a community, we can afford to do the material science studies. You can afford to get people to tool and kit up to start manufacturing things out of products and out of materials that are much more fit for purpose. I'd like to see no more cable ties being used. But at the moment, we don't have an alternative to cable tying. So we have been testing a few of these things this summer. We had a crack at just making sure that we could recruit in exactly where we wanted to, and we tried a few methods. They clearly like little cavities, we knew that. In fact, we have a been doing a collaboration with Seeker. We've got a whole stack of their devices where, again, we're just doing some stuff just to understand what the mortality rates are in the GBR context, because no one's used these. WhenX for us, that's one example of what we've covered, what we put under our core aquaculture thing. We've got others that we're working on in that same space, but we've been doing similar sorts of things to a lesser degree across all of these things, understanding how you might put geoengineering, so cloud brightening systems out there, how we might work on some of these methods to collect larval slicks and deposit them in the location that might work. And so we're going to be doing a bunch of field testing on a repeat for other intervention types, looking at the synergies between them. We've started doing this and doing some operations research. Infrastructure deployment costs are really quite significant component. If you can leverage that, so if we could use boats that were doing aquaculture deployment to then go and do larval slick capture for part of the year and repurpose them for that, you really start getting some economics of scale into the system. Importantly, in the GBR context, we need to think about our commercial and business models. Lots of things that I'm talking about here need big capital investment. You're not going to get that unless you've got a business framework. We've got to bring this into a commercial context. And of course, we're learning from it. So a final slide. I might have done this a bit quickly. Amazing. It's unusual for me. Ecosystem scale restoration. People go, is it possible? I actually think it is. I think the challenges are in the ecology and the biology and the genetics and all that sort of stuff. There's a huge latent engineering capability that's sitting out there that just has not been leveraged into this space yet. And I don't say that to put any of the efforts down to date. We just haven't actually had a crack at doing this as a community. And Australia hasn't because we haven't needed to. We have to now. We're definitely thinking in this space, and we're going to give us a go. I like to have the Lego thing in there. They make a truly enormous number of those every day. Hundreds of millions. It's just crazy. There's manufacturing stuff out there. There's automation. All the things that we did in this design were off the shelf. Just repurposing. Yeah, sure, we've got a few things that we needed to crack. We did some assessment of what's the feasibility that we think we might get out of season spawning in place so we could do multiple tranches. But we also backed that up with some microfragmentation assessments about could we use that as an alternative method if we can't develop that. So a few final conclusions, I guess. My strong advice is utilize existing technology. Invest only in the gaps. There's a bunch of people out there that have been building this stuff, that have been doing it for years. Let's think we can do better than what's in the system at the moment. But focus our efforts on the gaps. We do have to embrace modern manufacturing methods. If you're going to go to scale, you've got to start thinking about that. What I should have mentioned at the start was one of the ground rules we had for this design is that you weren't allowed to be in the water. So we had to think of ways that kept people out of the water. And that's not to take the human out of the loop, right? But in our context, we simply were never going to be able to put enough divers in the water. It's too remote for the types of scale that we're talking about. And so we haven't cracked all of those things yet, but what we do know is the bits that we have to crack. So it gives us some focus. Standardise, modularize, if that's actually a word, I wasn't sure. I'm an engineer, not a literary professor. And automate. Key. For those that are a bit older in the audience, you might remember the VHS beta days. I'm hoping we can do better than that as a community. We're a long way from being at a point where we can make those sort of calls, and it won't be one choco block size or something like that, but it ideally will be a suite of them, because then we can start leveraging mass production. You can start tooling up and building little gadgets that will work in different contexts, and you can bring the price down. And finally, consider scale from the start. I don't have time to go through this today, but in a number of the cases we've been doing assessments, they look great until a point, and then you just run into this, oh my goodness, barrier that the price all of a sudden goes up. And so you need to think those things through. So a few acknowledgements, just to finish up. The Wally Parsons team, Mark Gibbs from Q2 dug me out of a bit of a hole. I took on more than I could chew with leading this program and running this area as well. Dirk Peterson and the Seacore team, and most importantly, Andrea Severetti from AIMS, who's an accurist but a better engineer than me. Most of those design ideas and all those drawings are his. and no, you can't have them. So thank you, everybody. I hope that gives you a bit of an idea.
Thanks, David.